In this presentation, I'll be explaining the closed loop configuration of operational amplifier, in which we'll be seeing the inverting amplifier, non-inverting amplifiers, and then voltage follower and differential amplifiers. Let us see the closed loop configuration of operational amplifier as an inverting amplifier. That will be inverting the signal, that is amplification as well as inversion is also taking place. Therefore, this is an inverting amplifier in which the signal to be amplified is given to the inverting terminal through an input resistance R1, and from the output there's a feedback resistance RF that is connected to the inverting input, and non-inverting input is grounded. And here this is an ideal inverting amplifier, and in this one it is marked as the current input to the op amp, that is I in, it is marked. Ideally that is equal to 0, that will be 0, it's marked as I in, and this is the I, and this is the IF, feedback current, and this is the point at which the both resistance, feedback resistance and resistance are meeting, and that is connected to the inverting terminal. Now the input signal is amplified, is applied. The input signal is applied to the inverting input through resistance R1, and a resistance RF is connected between the output and the inverting input as the feedback resistance. RF is connected as a feedback resistance. Input resistance is equal to R1. Now, applying the Kirchhoff's current law at the junction A, here the current is entering equal to I, and here the feedback current, and I in is the current that is going to the op amp. Now, applying the Kirchhoff's current law to the point, to the node at A here, applying KCL at the junction A here, current coming towards the junction, that is II plus IF, that is equal to I in, current leaving from the junction. Or, as you know that one, the input impedance of this op amp is, ideally it is infinity, or it is very large. That is why the input current to this op amp equal to can be approximated as 0. I in can be approximated as 0. Therefore, I plus IF, which is equal to I in, that is equal to 0. Therefore, I plus IF equal to 0. And one more thing is that here, if you consider the ideal op amp, the open loop gain of an ideal op amp is infinity. Then open loop gain of this op amp is nothing but it is equal to V0, output voltage V0, divided by whatever the voltage at this non-inverting terminal, V plus minus V minus, that is equal to infinity. Or you can say that one, V plus minus V infinity, V minus, V plus minus V minus equal to V0 divided by infinity, or that is equal to 0. Meaning that V plus equal to V minus, that is the voltage at plus same as V minus, or voltage at V minus is same as whatever the voltage at the non-inverting terminal. That is why this ground point is, this potential is same as this potential. That's called the virtual ground. This voltage is same as this voltage because V plus is same as V minus. Therefore, this is a virtual ground. This voltage is equal to 0 voltage. Since it is grounded, this voltage VA is equal to 0 voltage. Now, coming back to this one, we can get I1 plus IF equal to I in, which is equal to 0. And since the voltage at this point equal to 0 voltage, the ground voltage, applying this theorem, and the voltage at the V minus ground voltage, and this is called the virtual ground, or that is equal to voltage at A. Voltage at A equal to same as the ground voltage. Now we can apply the, you can write the equation for the current. Current I is nothing but V in minus VA. V in minus VA divided by R1, and that plus whatever this current IF is equal to V out, that is output voltage V out minus VA divided by RF. That should be equal to 0 because input current to the op amp is equal to 0 because input resistance or that is equal to infinity. Therefore, I in is equal to assuming as 0. Therefore, that is equal to 0. Or also we have seen the voltage at A is same as the ground voltage, that is equal to 0. Substituting that VA as equal to that is voltage at V minus as equal to 0. Here we will be getting V in minus 0 divided by R1 plus V out minus 0 divided by RF, that's equal to 0. Or we can get it as from this equation V out divided by V in, that is output voltage divided by the input voltage, that is equal to minus of RF divided by R1 minus RF divided by R1. Therefore, the gain of this inverting amplifier is given by minus RF divided by R1. That is closed loop gain of an inverting amplifier, ACL, it's called ACL, is equal to minus RF divided by R1, where RF is the feedback resistance, R1 is the input resistance. And this negative sign indicates, that there is a phase shift of 180 degree between the input and output. Therefore, here between the output and input there is a 180 degree phase shift, and the magnitude of the output voltage is equal to minus RF divided by R1 times the input voltage. This is the operation inverting mode. This operation amplifier is working as an inverting amplifier. Continuing the inverting amplifier circuit, here same circuit, here op amp circuit, feedback resistance RF, input resistance R1, and the gain is given by minus RF divided by R1. And assume that the inverting amplifier gain is equal to 10 or minus 10. Design an amplifier with a problem is design an amplifier with a gain of minus 10 and input resistance equal to 10 kilo ohm. This is the question. Therefore, the gain equal to minus RF R1, that's equal to 10. Or R1 is taken as, say we are taking the R1 is taken as 10 kilo ohms. Therefore, R1 is taken, this R1 is taken as 10 kilo ohms. And now we can substitute this one. The gain should be equal to the magnitude of the gain equal to 10. Therefore, it is equal to 10 equal to RF divided by R1. Or you can get RF is equal to 100 kilo. Therefore, to get a gain of 10 with for inverting amplifier, this is taken as 10 kilo ohm and RF is taken as 100 kilo ohm. Therefore, the gain is given by 100 divided by 10. 10 is the gain. But if you are applying a 1 voltage here, you will be getting here it is equal to minus 10 volt. 1 volt sinusoidal if you apply here you will getting minus of 10 volt sin omega t, minus 10 sin omega t. Therefore, here as an example, here it is shown here. The voltage is applied with a here plus 5 maximum plus positive side and minus 5 minus for total peak to peak equal to 1 volt is applied here, and this is equal to 1 kilo and this is also equal to 1 kilo. Then if you see the as per this equation 1 by 1, the gain is equal to unity or RF by R1 equal to unity, but there is a phase shift is there. Therefore, this output will be inverted version of this one. This will become equal to, when it is positive, this will be negative. When it is negative, that will be positive. For inverted version of this one, with a gain of unity, but minus 1 is there. That's why inversion is there. And another example we have seen with a gain of here. Now in this example, you can see an op amp with a feedback resistance 40 kilo ohms and input resistance equal to 1 kilo ohms. Therefore, the gain if you calculate RF by R1, it is equal to 40 is there. And input voltage is equal to here positive side plus 0.5, minus side it is minus, negative side minus 0.5. Therefore, if it is amplified with this gain, you will be getting actually the gain is equal to 40 divided by 1. 40 is the gain of minus 40 is the gain. Therefore, if you multiply with the positive side 0.5 with the 40, you will be getting it is equal to 20. Positive side 20. Similarly, negative side also equal to 20. It should have been 20 peak value of sinusoidal with the inversion of this one. When during the positive half cycle it should be negative, and during the negative half cycle the input should be positive. But one point is that the output voltage never goes more than the biasing voltage. Therefore, the biasing voltage equal to plus 15 and minus 15 here. Therefore, you cannot go above that one, even though the gain is equal to say 40 and input equal to 0.5. 0.5 into 40, it would have been 20, but you won't get 20 volt. Maximum voltage you can get is equal to the biasing voltage, slightly less than biasing voltage across the drop across that RC, everything comes. Therefore, the output voltage will be between somewhere less than that VCC, slightly less than that VCC, maybe 13 volts, in between 13 and 14. In that range, it will be getting. Therefore, here the output voltage, if it is going more than that value, that gets saturated. That is why here, rather than going up to the 20, it is getting saturated after say 13 plus 13 volt. Similarly, here minus 13 volt. That is getting saturated. That is because the output voltage is going more than the biasing voltage. If you won't get an output voltage more than bias voltage, that should be careful in the case of a op-amp amplifier. It is an inverting amplifier. And next we are going to a non-inverting amplifier, in which the signal is applied to the non-inverting terminal, that is plus terminal, and the feedback is connected, feedback resistance RF is connected between the output and the inverting terminal negative, and this is one other resistance R1 is grounded, and here it's called a non-inverting, means output voltage is having the same phase as the input voltage, and we'll be deriving what is the gain of the amplifier. That is similar to the previous one here. This is I marked as the II, and this is IF, and this is IN. And as I explained the previous slide, the input current is 0. IN equal to 0 because input resistance is very, very large. You can take it as infinity, so that this input current equal to 0. Therefore, applying the Kirchhoff's current law to this point, we'll be getting II plus IF equal to IN, which is equal to 0. II plus IF is equal to 0. That is, we'll be getting, applying the II plus IF is equal to IN, IF plus II equal to 0. That is the first, applying the Kirchhoff's current law to the node, to the point, to the junction A. Another point is that, as we have seen here, the voltage at this inverting terminal is same as the voltage at the non-inverting terminal. That is because the open loop gain of the amplifier is equal to infinity, which is equal to V out divided by V plus minus V minus, or V plus minus V minus equal to V out divided by infinity, which is equal to 0, or V plus equal to V minus, or you can say that V minus equal to here V plus, which is equal to V in. Therefore, the voltage at the point A is same as V in. That is the second point. Voltage at the point A equal to V in, and we are going to apply, apply the Kirchhoff's current law based on this voltages, and then applying this one here for an ideal op-amp, open loop gain is infinity. That is why we have seen V plus equal to V minus. We will be getting the voltage at this plus is same as V in, or this V in is equal to the V in, that is this voltage. Voltage at the point A is equal to V in. Applying the Kirchhoff's current law, as I told you, this II plus IF is equal to IN, which is equal to 0, or IN equal to 0. That now we are going to apply this this Kirchhoff's current law by giving the by giving the voltage by current ratio here. Therefore, the current which will be getting, this one is equal to this voltage. This is, if you take this current, you can write it as a 0 minus VA, 0 minus whatever this voltage VA means, this voltage, this is same as V in voltage. VA is same as V in. Therefore, it is equal to 0 minus V in divided by this R1 plus here V out minus V in, V out minus V in divided by RF. That should be equal to the I in, which is equal to 0. Or this can be written as minus V in divided by R1 plus V out minus V in divided by RF is equal to 0. Or you can write it as V in, V out divided, we are grouping that, V out divided by RF equal to V in into 1 by R1 plus 1 by RF. That is V out divided by RF. Or we can say that V out equal to 1 plus RF divided by R1 into V in. Or the ratio of output voltage V out to the input voltage V in, V out divided by V in, which is equal to 1 plus RF divided by R1. Therefore, the gain of a non-inverting amplifier is equal to 1 plus RF divided by R1, 1 plus RF divided by R1. And since the phase there's no phase shift here. That is why it is a positive. For output voltage is equal to 1 plus RF divided by R1 into the input voltage. Whatever the voltage applied here, that into 1 plus RF divided by R1, that is the output voltage. That is called the closed loop gain of a non-inverting amplifier. For the closed loop gain of a non-inverting amplifier is given by 1 plus RF divided by R1, where RF is a feedback resistance and R1 is a resistance that is connected to the ground from the inverting terminal. This point, this is the R1. Now, for the positive sign indicates that there is no phase shift between the input and output. That is why it is called a non-inverting amplifier. The phase of the output is same as the phase of the input signal. There is no phase shift. Now let us see a circuit of what we call it as voltage follower. Voltage follower using an operation amplifier, in which it is a modification of a non-inverting amplifier, in which you are giving the signal to the non-inverting terminal plus terminal, but here the feedback resistance is made 0. That is, you are shorting this one. RF is made 0. Similarly, there is no resistance that is connected to the ground, or we can say that one R1 is made infinity. You are making R1 made infinity and RF is made 0. Applying to that one as a non-inverting amplifier, the gain is equal to 1 plus RF divided by R1. Therefore, 1 plus RF is equal to 0 and R1 equal to infinity. 1 plus 0 by infinity, that's equal to gain. Or the gain of this amplifier is equal to unity. Both, there's no phase shift as well as the magnitude is same as the input. Whatever the input signal you are applying, the same signal will be available at the output. That's called the voltage is following. Output voltage is following the input. That is why we call it as voltage follower. For the voltage follower circuit is a special case of non-inverting amplifier where all the input is fed back into the inverting input. All the output, where all the input is fed back to the, it's a mistake. So all the output, whatever the output, this is all the output. Whatever this output is fully fed back to the input, and here the closed loop gain, as we already derived 1 plus RF by R1. But in this case, RF is equal to 0 and R1 is equal to infinity, or you will getting 1 plus 0 by infinity equal to gain equal to 1, or meaning that output voltage is same as the input voltage. Gain equal to unity means whatever you are giving the input signal, the same thing will be available at the output, or the output voltage is equal to the input voltage both in magnitude and phase. It is equal to the input voltage both in magnitude and phase. That means that output voltage follows the input voltage. That is why this is called a voltage follower circuit. This is called a voltage follower circuit, in which there is no feedback resistance is made 0 and input resistance is made infinity, and it is a modification of a non-inverting amplifier, and this circuit we call it as voltage follower. Output voltage is same as the input both in magnitude and phase. Now let us see a problem. Here the circuit diagram is given, is a inverting amplifier, feedback resistance 100 kilo and input resistance 10 kilo ohms, 1 volt peak to peak, that is the voltage that is applied at the input side, and here biasing voltage are the load resistance is 10 kilo ohms, and this is a inverting amplifier circuit. The question is that for the circuit shown by figure, what is the closed loop gain? That is the closed loop voltage gain is to be found out. First one. Second, what is the input impedance? Third, what is the maximum operating frequency that can be operated? What can be the maximum frequency of the input signal for this inverting amplifier? And the slew rate is given as, this is a IC741. It is given as 0.5 volt per microsecond. These are the data given. Now let us first see the closed loop voltage gain. Closed loop voltage gain for an inverting amplifier is given by, it is equal to, it is equal to minus RF divided by R1. It's an inverting amplifier, minus RF divided by R1. Therefore, if you take it as, it is equal to minus 100 divided by 10 kilo ohm, or equal to minus 10. Therefore, the output voltage equal to minus 10 times the input voltage. There's a phase shift of 180 degrees there, and magnitude is equal to 100 times the input voltage. Therefore, the input impedance is that. Input impedance, looking from this one, what is the input impedance? The input impedance of the op-amp equal to infinity. This is the input impedance is infinity. But since you are connecting a resistance externally between the source and the non-inverting terminal, if you draw the equivalent circuit here, AC equivalent circuit here, we get this resistance, this R1 will be coming in parallel to that one. That will be coming in parallel to the ground. Therefore, looking from this one, the input resistance, total input resistance of this inverting amplifier, that is same as R1. It is the R1 will be coming in parallel between this point and the ground. For 10 kilo ohm is the input impedance, or that is the input resistance. The next one is that the input voltage equal to 1 volt peak to peak, and the gain is equal to minus 10. Therefore, the output voltage will be equal to the input voltage into the gain. Therefore, 1 volt peak to peak into 10, or that is equal to 10 volt peak to peak. Therefore, the output voltage magnitude will become 10 volt peak to peak. 10 volt peak to peak means that peak value will be equal to 5 volt. Therefore, the peak output voltage is equal to 5 volt. So, peak to peak voltage equal to 10 volt, and peak voltage will become, that will be changing from plus 5 to minus 5. The total change is equal to 10 volt, and peak voltage and peak to peak voltage equal to 10 volt. And here the maximum value of the voltage in one direction is equal to 5 volt. Now the question is that you are asked to find out maximum operating frequency. Slew rate is given. Already we have derived the equation to find out the maximum frequency, which is equal to slew rate divided by 2 pi into V peak to peak. V peak. 2 pi into V peak. And V peak is already found, it is equal to 5 volt. Therefore, slew rate is given as 0.5 volt per microsecond. Therefore, 0.5 volt per microsecond divided by 2 pi into peak voltage, that is equal to 5 voltage. And you will be getting it is equal to 15.9 kilohertz. For the maximum frequency for which this IC741 can be operated with this peak value, that is 5 volt value, that is equal to 15.9 kilohertz. That is the answer. Maximum operating frequency equal to 15.9 kilohertz. That is decided by the slew rate of the op-amp circuit IC741, that is equal to 0.5 volt per microsecond. This is another problem in which actually this is a non-inverting amplifier, and you are asked to find out what is the output voltage, and input voltage is given as 1 volt. The input voltage you given as 1 volt. What is the output voltage, and the feedback resistance is 50 kilo ohms, and the resistance at the input side, which is grounded, it is equal to 10 kilo ohms. And here 1k and 1k are the resistance, that is voltage divider it is working, and you are asked to find out what the output voltage. First you have to find out what is the voltage coming at the non-inverting terminal. V plus, what is that voltage? What is the voltage coming at this point? Because there are two resistance, they are connected as a potential divider. Therefore, the voltage at this input, that is the voltage at the non-inverting terminal, that is this terminal, we can say VA. Voltage at this terminal VA equal to whatever the input voltage divided by R1 plus R2 into R2, or whatever this voltage divided by 1k plus 1k into 1k. Therefore, this voltage into 1k plus 1k plus 1k divided by 1k plus 1k into 1k, or that's equal to 0.5 volt. So the voltage at this point is equal to 0.5 volt. Once you get this voltage at VA, which is equal to the non-inverting terminal, the output voltage is given by 1 plus RF by R1 into this VA, or whatever the voltage at the non-inverting terminal. Therefore, the output voltage is given by this, whatever this voltage at the non-inverting terminal, that into 1 plus RF divided by R1. Therefore, 1 plus RF by R1 into VA, that is equal to output voltage. Therefore, 0.5 into 1 plus 50 divided by 10 kilo ohms, which is equal to, we'll be getting it is equal to 50 divided by 10, 5, 1 plus 5, which is equal to 5 plus 1, 6, 6 into 0.5, 3 volt. The output voltage is equal to plus 3 volt. Therefore, when you apply a voltage of here V in of 1 volt here, you will be getting a voltage, output voltage of plus 3 volt at the output of op-amp. This is a non-inverting amplifier operation. Now let us see the closed loop operation of an operation amplifier as a differential amplifier. In that one, there are resistances like here feedback resistance RF and R1 is connected, and this junction is connected to the non-inverting terminal, and non-inverting terminal again the point B. This is a point A, this point B. Here again the second voltage, here the voltage is V1 and here the voltage is V2. V1 is connected, anyone that this resistance equal to, say it is marked as R2, it is not RF, R2 and R1, and here also R2 and R1, this voltage equal to B, and the voltage at this point equal to V1 and this is equal to V2, and the voltage at this coming voltage which is equal to V3. The same voltage will be coming at this point because of the virtual ground property. Now let us analyze that one. There are two voltages V1 and V2. Now from the when one thing is that in order to find out the output voltage, first voltage is present. You assume that first V1 is present and V2 will be grounded. Then you will be seeing what is the output voltage. Then next second case you will be V2 will be present and V1 will be grounded. Then what is the output voltage? When both are present is equal to the sum of these two. That is called the superposition theorem. And coming to that one, if here applying the KCL at the point A, that is at the point if you apply the Kirchhoff's current law to this one, we will be getting it is equal to V1 minus this voltage. This voltage I am marking it as it is equal to V3. V1 minus V3 divided by R1, that is this current, plus this current. The here this is a V1. This is V1 and this is V2. For V1 minus this is equal to V3. V1 minus V3 divided by R1, that is applying this one, plus here V1 minus V3 minus V0 ground voltage. What is this one? This is a V3 minus V0, that's the ground voltage, divided by this resistance R2, that is equal to 0. Or similarly, if you apply, applying the KCL at the point here, we'll see. Therefore, in this differential amplifier, as we seen, this is the voltage V1, this is equal to V2, and this voltage equal to V3, and this is equal to V3, and this is equal to R2, this is equal to R1, and this is equal to R2, this is equal to R1, and the output voltage. And we are going to apply the Kirchhoff's current law to the junction. First, we will be applying to the junction A, and next we will be applying to the junction B. Applying the Kirchhoff's current law to this junction A here. Here what we are taking that this current plus this current equal to this current, because this current equal to 0. That is why we are equating this current plus this current equal to 0 we are taking. Therefore here we are taking this is V3 minus V2 divided by R1, V3 minus V2 divided R1 plus V3 minus V0 output voltage, V0 divided by R2, that's equal to 0. We are applying the Kirchhoff's current law to this node A. Similarly, applying the Kirchhoff's current law to the node B here, again this current is given by here V3 is the terminal voltage, this voltage, V3 minus V1 divided by R1 plus this current V3 minus 0 or V3 divided by R2, that is equal to 0. Therefore, we are applying the Kirchhoff's KCL, Kirchhoff's current law at the node A and B, and we are writing the equation 1 and 2. And from the equation 1, we'll be, if you are grouping this one, we'll be getting V3 into 1 by R1 plus 1 by R2 minus V2 by R1 equal to V0 by R2. That is from this equation you are deriving this one. Similarly, you can derive the equation from the equation 2, grouping the here V3 into 1 by R1 plus 1 by R2 minus V1 by R1 is equal to 0. Therefore, from this equation 3 and 4, or if you minus 3 minus 4, that will be getting it is equal to V2 by R1 plus V1 by R1 equal to V0 by R2, or we can get it as it is equal to V0 by R2 equal to V1 minus V2 into R1, or output voltage is given by V0 is given by R2 by R1 or R2 by R1 into V1 minus V2. the difference in voltage V1 and V2 is taken, the difference in voltage is taken, that is multiplied by R2 by R1, that is the output voltage. Therefore, V0 equal to V1 minus V2 into R2 by R1. Therefore, this type of circuit is very useful in detecting very small difference in signals by selecting again this ratio R2 by R1 very large. Say for example, if R2 equal to 100 times R1, then a small difference in voltage V1 minus small difference in voltage, that is amplified as 100 times. So for example, if there is a small change of 10 millivolt change here, that 10 millivolt into 100, that will become 1000 millivolt or 1 volt. Output voltage will become 1 volt. Therefore, you can amplify the difference in signal V1 minus V2 with the ratio R2 by R1. That is called the differential amplifier. The difference in signal V1 minus V2, that is amplified with a ratio of R2 by R1. That is, since it is amplifying the difference in signal of input V1 and V2, this is called a differential amplifier.